So our next speaker is Shai Shalev-Shwartz from Hebrew University and Mobileye, who will talk about, is deeper better only when shallow is good? Thanks, Shai.
Thanks, Amir. Hi. It's going to be a technical talk. You will not see autonomous driving. It's about deep learning. The first word in deep learning is deep. And I will start with a blog post by Joel Grus. He describes an interview that he's going through in some company, and the interviewer asked him to print the numbers from 1 to 100, except that if the number is divisible by 3, print fizz. If it's divisible by 5, print buzz. And if by both, print fizz buzz. A classical question to ask in an interview for coding. Do you need some help? No, I'm good. Let's start with some standard imports, and then you import TensorFlow and NumPy. To those of you who don't know, TensorFlow is a package for deep learning, and obviously this is not the right solution for this problem. And he described it's very funny. At the end he says, I didn't get the job, so I tried actually running this, and it turns out it got some of the outputs wrong. Thanks a lot, machine learning. And then he ends up by the ultimate answer nowadays. I guess maybe I should have used a deeper network. So today, deep learning, you need to go deeper, 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 more data, deeper. So the topic of this talk is about depth efficiency. A basic question, do we really need a deeper network? A different question, on which distributions deeper networks are actually much better than shallow ones? And there are many theoretical results around this problem. Basically, most of them looks like the following theorem. There exist functions which can be expressed by a small deep network. Small means that the number of neurons overall in the network is small, not, say, polynomially in the input size and not exponentially large in the input size. So there exists functions which can be expressed by a small deep network, but must have an exponential width in order to be expressed by a shallow network. So in this case, in order to learn these networks, you expect that you need to go deeper. And there are many results formalizing this argument. And what I'm going to argue in this talk is that if this is the case, if you need strong depth separation, if there is strong depth separation, if indeed you need a deeper network in order to learn, and you cannot learn the problem with a shallow network, then maybe it's good for deep networks, but it's not good for the basic algorithms that being used for deep learning, which is stochastic gradient descent, or actually any gradient-based algorithm will fail. So strong depth separation is bad. It's not a good thing, it's a bad thing. This is the main message of this talk. Now you may ask, is it practical? So should we go back to shallow things? The answer is no. But there are some consequences of this theory, and I will try to touch them at the end of the talk. So in order to talk about depth separation, I chose a very basic construction, fractal distributions. These are very natural creatures for studying depth in neural networks. Then I will show depth separation results, which is not interesting by itself at all. It's yet another depth separation result. The only purpose of this result is to continue and discussing approximation curve and strong depth separation, which is maybe the ultimate depth separation that can exist. It means that you can do nothing with shallow network, but you can express a problem with a deep network. And then the main argument of this talk is that success of SGD depends on the approximation curve, and if the approximation curve is very sharp, so if there is a strong depth separation, then gradient-based algorithms will fail and will not be able to learn the problem at all. So this is the outline of our talk. So let's start with technical things. Fractals. We discussed a specific form of fractals, which is called IFS, Iterated Function System. You start with the set of cube in RD, and then you define the next set in a recursive way based on the previous set by applying R functions, F1 to FR. Each one of them is an affine function, invertible, contrastive, and two disjoint functions have disjoint images. For example, what you see in the image at the end, K0, this is in R2, so K0 is just a square, and then you apply shrinking linear operators F1 to F4. Each one takes the square and take it to one of the corners, and then you repeat it recursively, and then you get a fractal. And the depth of the fractal is how many times you iterated this process. So what is a fractal distribution? A fractal distribution is simply a distribution in which positive examples are from the set Kn, from the fractal, and negative examples are from the complement of the fractals. So for example, you see a Cantor fractal on the left-hand side, and you see two colors. One of them is from the fractal set, and the other examples are sampled from the complement set. Okay, so why fractals are so nice? Because you can prove for fractals very easily depth separation. So in order to show depth separation, I will first show you that a deep network can realize fractals distributions. And then on the next slide, I will show you that a shallow network cannot realize fractal distribution. So we will have depth separation. Deeper networks can realize a distribution, while shallow networks cannot. So the first side, consider an IFS in D dimensions with R generating functions and depth n. And to remind you, a fractal distribution, which I denote here by D sub n, is a distribution where the positive examples are from the fractal set and negative are from the complement of the fractal set. So for any fractal distribution, the theorem states that there exists a ReLU feed-forward network of depth 2n plus 1. So the depth is order of the depth of the fractal. Width is 5dr. D is a dimension and R is the number of generating functions. So the width is also small. It's linear in the relevant dimensions. And this ReLU feed-forward network realizes the fractal, meaning that you can classify examples completely to say whether they are positive or negative by a network of depth n. And how do you prove this? Like we prove most of the nice things in mathematics using induction. So the basis of the induction is to show that a ReLU network can approximate the cube, and intuitively ReLU is just taking a half space. So you can easily take a half space for each of the sides of the cube, and by that you approximate the belongness to the cube. And then the construction is really 4 bullets, so I will do it quickly. Suppose that we have already constructed a deep network that expresses the set Kn minus 1, so this is a level n minus 1 that we constructed in the fractal. So we can have a network that indicates whether we are on this set or not. Now, if we take the set Kn, each element in Kn is obtained by applying some of the Fi on the previous set, on Kn minus 1. But Fi are affine functions, and they are also invertible. So we can look at the image, and we can take for every such x, we can find z in the previous fractal set, and the function I, such that x is simply Fi applied on z, but we can invert the function, so z equals Fi minus 1 on x. And once you see this, it's really trivial to see that by combining these values, applying ReLU, we obtain an indicator of the next set, so we completed the inductive argument. So this theorem tells you that we can express fractal distributions of order n by deep networks of order n while maintaining a small network. The overall number of neurons is small. On the other hand, to show depth separation, we need to show that a shallow network cannot express this fractal distribution. So the second theorem is that if the distribution has non-zero probability in any area of the fractal set, for example, a uniform distribution, then a network of depth t needs to have widths which is order of r to the n over td. So t must be order n, otherwise we will need a very, very wide network, an exponentially wide network, and hence we get depth separation. And the proof of this theorem is also pretty straightforward. It's just a counting argument. So we can count network of widths k and depth t. We can count how many linear regions it can express as. And we can also see that a fractal distributions need r to the n linear regions. So just comparing the two, we obtain the theorem. Okay, so what we have shown so far, we have shown that what are fractal distributions, and we have shown a depth separation result for fractal distribution, showing that a deep network can express the fractal distribution, while a shallow network cannot. The next step, in order to show that strong depth separation is bad, the next step will elaborate on how much is the difference between deep and shallow networks in expressivity of the distribution. We will talk about the approximation curve and strong depth separation. Okay, so what is the approximation curve? Approximation curve is simply how much of the negative examples are on the fine details of the fractal. And formally, it's just the 1 minus the loss of the indicator function of the jth set in the construction of the fractal. So we have a fractal of order n, and we try to approximate it by the jth set. So obviously, if we start with p0, we get an accuracy of 1/2. And if we go to pn, we get an accuracy of 1 because we can express the fractal distribution completely by the kn set. But the question is how this function, the approximation curve, progresses in time. So here are two examples. On the left-hand side, you see a distribution. In both of the cases, both left and right, it's a contour, two-dimensional contour set. And on the left side, most of the negative examples are on the coarse details of the distribution. There are some negative examples on the fine details, but there is also a lot of negative examples on the coarse details of the fractal. On the right-hand side, all the negative examples are on the fine details of the fractal. So in the left-hand side, even if we take a network of depth, not very deep, a shallow network, then we gain something. We are not at a 1/2. We are a little bit better than random, and we are becoming better and better until we get to 1. On the right-hand side, if we take the j set at the beginning for small j, we do not express anything because all the details are on the fine details of the fractal distribution. So I don't have a lot of time, so this theorem just tells you that indeed this approximation curve is indicative as to what the best network of a certain depth will approximate the distribution. So roughly, if you take a depth t network and t is 2j plus 2, then the loss of the best network is roughly 1 minus p of j. It's upper bounded from above by it and from below up to some factor which is very close to 1. All right, so now we can move to the main claim. So to explain the main claim, I will take an even simpler example, a one-dimensional counterfractals with fine distributions. So it's explained by this picture. So we take 1/3 out every time, and then we put all the negative examples on the fine details of this distribution. So the theorem says that if we consider a network of depth t and the fractal of depth n, then if t is significantly smaller than n, then all the elements of the gradient at the initialization for any normal initialization will be upper bounded by 5 times p of j minus 1/2. This means that if the fractal distribution is focused or concentrated on the fine details of the distribution, then p of j minus 1/2 will be 0 for any small j, and then the gradient will be almost 0 at the initialization. So we will not be able to learn even a deep network. If there is a strong depth separation, we will not be able to learn it. It's just an illustration of how does it look in practice. So this is, again, the same Cantor set. Now it's two-dimensional, and depth 5. And we're trying to learn with different approximation curve. Approximation curve number 6 is with a strong depth separation. That is, you are almost at 1/2, and then you grow sharply to 1, as opposed to curve number 1. And the practical performance is that as you move on the curves, the performance is worse and worse. So is it only on synthetic data? So we conjecture that this situation is true also on real-world data set. And actually, if you look at real-world data sets, for example, this is an example of CFAR10. If you train convolutional neural networks with deeper and deeper networks, you don't see a strong depth separation. You see that even shallow networks do something. Okay, so yes, we do not get to 85%, but we get much better than a random guess already with a shallow network. So, to summarize, fractal distributions are a very elegant way to study depth efficiency and deep learning. And the main claim that we want to make in this work is that if you have strong depth separation, it's very nice theoretically, but it will not, you will not be able to train your model using gradient-based algorithm. And we conjecture that this is not only for fractal distribution, but this is actually true for most distribution. In other words, deep is better only if shallow is also not too bad. Thank you very much. Yeah.
Do you have any recommendation for areas where the shallow nets fail?
Any recommendation? So, oh, other algorithms. I'm not sure there is a general. So the question was, if we have strong depth separation and gradient-based algorithms fail, do we have an alternative algorithm that will succeed in these cases? In general, the answer is no. As far as I know, we don't have good algorithms other than gradient descent. There are some esoteric cases in which there are known algorithms which perform better than gradient descent, but I think these are the exceptions and not a common thing. And maybe everybody wants to go to the coffee, so I will take more questions offline. Thank you very much.